Today we will continue with chapter number 7, Induction Motor. Okay. So in this chapter we will be covering four important parts of induction motor. The first thing is the induction motor construction, the principle of operation of the induction motor, torques are involved in the motor, and also torques versus slip characteristic. Okay, so before we start, we just try to compare with the DC motor that we have studied before this. In DC motor, we know the structure, so it will have two types of two parts. The first part is the stator, which is the stationary part. So, the stationary part usually will be the outside of the motor, and we have the rotor, which is the inner rotating part. Okay, so the rotor is actually what rotates in the motor, DC motor. Okay, so in the picture we can see the red color. We call it as a not polarization because it involves magnet. Okay, and the green represent the south. Okay, and you can see in the middle. So you have the rotor, and it will be energized to become either green or red. Okay, so as we know, magnets usually will attract the different polarities. So red will attract green and green will attract red. Okay, so that is how the DC motor will rotate. Okay, so we can see here we have six poles. So all the poles will be energized in order to make it rotate. Okay, so this is the DC motor structure. So let us see the AC motor or AC machine construction. Okay, just like a DC machine, AC machine also consists of a stator and also rotor. Okay, so you can see the parts of AC machine. So this is generally the rotor, the middle part of the AC motor, and this is the stator. So you can see it has a lot of coils and also a place to put the rotor. Okay, so if we see in AC machines, especially the stator, the outer stationary steel frame enclosing a hollow cylindrical core. So usually it will be like this. So a place, a mounting, and also for three phase. So if the AC machine, because AC machine we usually will be dealing with three phase. Okay, so it has a three phase of winding. So if you still remember, so for three phase, we will have three separate winding separated by under 20 degrees. So similarly, inside all the wiring will be in a three phase construction. Okay, so the greater number of poles, the lesser is the speed, and vice versa. We need to understand. So it's not number the greater the number of poles, the more the speed. Actually, when the number of poles are more, so there will be more frictions and there will be more switching of polarization. So it will make the speed of the motor to reduce. Okay, so the three-phase supply induces rotating magnetic field. Okay, so when it energizes, it will create a rotating magnetic field inside, and we know. So when the rotor is inside, so the distance between the stator and also rotor will create a air gap. Okay, so meaning there's a air gap in between. So usually it will be 0.5 millimeters, very small, but it makes a lot of differences, and up to 4 millimeters. Okay, so usually the closer it is, so the more the power of the motor. Okay, so the types of rotor. So usually the squirrel cage. So as you can see in this picture, so this is the most common form of rotor. Okay, so if you see, you can see the laminated cylindrical cores with a parallel slot in the outer periphery, and also it has a metal rings called end rings. Okay, so you can see inside. Okay, so it operates based on the transformer principle. Okay, so I believe all the transformer and also the AC parts are using almost the similar principle, the energization of the EMF, electromotive force. Okay, so the squirrel cage, what is the advantage? It is actually a simple construction and it also a robust construction, meaning it can be used for various applications. But it carries a disadvantage, which a low starting top. So we need to have a starting top, okay, in order to start the motor. So usually the squirrel cage, because the construction is very simple, so it will have a low starting top, and it's not possible to add external resistance. So usually we will have an external resistance to give a push, okay, for it to start. But since the construction is very simple, so you don't have the possibility to add the external resistance. Okay, and the second type we call it as a wound type. So it's actually a laminated cylindrical core, and it has. So we know AC is having star and also delta. So usually it will be a star connected three-phase winding. If an open ends are connected to three separate insulated slip rings, so three separate for three windings, three phase, and it carries an advantage. It has an increased starting top because you can add a external resistance. You can give a push, okay, for wound type. So of course it will be more expensive and not really common. Okay, so we'll see the operating principle of induction motor. Okay, so there are two key elements that we need to understand. First, the generation of a rotational magnetic field in the stator. So you have a stator outside and also rotor inside. So at first you need to create a rotational magnetic field in the stator, and it will cause the rotor to turn at a speed uh, dependent on the magnetic field rotation. Okay, so we know stator will not move, but the rotating magnetic field inside will make the rotor to spin. Okay, spin at a speed. Okay, so as a result, we can have a uniform rotating magnetic field produced in the air gap by balanced three-phase supply. Okay, so we can get that. Okay, so the next, the three-phase voltage system. So we know for three-phase, we have voltage generation and also current generation. And usually for three-phase, it will be separated by 120 degrees. Okay, so I believe you are still remembering this. So it is out of phase by 120 degrees, and the current also spaced by 120 degrees. Okay, so the formation of rotating field. Okay, so each coil produces sinusoidal flux distribution. So you can see here. Okay, so there are various type of amplitude, but it will be a sinusoidal like sine wave. Okay, and the coils are spaced under 20 degrees apart. You can see, so it's under 20 degrees apart, and sum of three winding contribution create a rotational flux. Okay, so we can see, so there are three, and when you sum it up, you can see it will move from one pole to another pole. Okay, and it will create a rotational flux. Okay, so flux is a rotating vector with constant amplitude. So it has a constant amplitude even though it is out of phase, but it has a constant amplitude. A stationary observer sees sinusoidally varying flux. Okay, so sinusoidally varying flux is very important because it makes the AC motor to rotate and it's possible. Okay, and the synchronous speed. The speed of rotating magnetic field depends on the number of excitation current is inside the number of poles in the stator. So previously we have seen. So the more number of poles, the speed will be lesser because you need to keep on switching. Keep switching. You need to make it green. Then you need to make this green, and you need to make the other part red. So it will make more steps involved, and of course it will create a frictions. Okay, and synchronous speed formula. So there are two formulas given. So one in revolution per minute and one more is in the radian per second. Okay, so this formula can be used to calculate. Okay, so rotor and stator interaction. Okay, so as we have understood from the previous slides, rotor and stator it has an interaction. Okay, so usually a rotor cannot catch up with the stator field. Okay, so we know stator is not moving, but there will be a rotating magnetic flux generated inside, which will be rotating, and it will automatically drag the rotor to follow. So it cannot catch up. So meaning the speed cannot be the same, or the position cannot be the same. So usually the rotor will be out of phase. So the stator field will lead. Okay, and rotor will follow. Okay, so that's why it's written here. A rotor is in constant pursuit of rotating field. Constantly will follow. Okay. So rotor speed depends on the number of poles. Torque magnitude is function of angle y between the stator and also rotor field. So we need to understand when there's a gap. Okay, so gap or angle between the stator and rotor field, then only is possible to have a torque. Because if we start at the same time, so it cannot create a torque or a power to rotate things. So it must have some gap in between. So it is important to generate a constant electromagnetic torque to avoid torque pulsation. Okay, so we need to have a constant electromagnetic torque. So we cannot like one time we generate 10 Newton meter. So one more time is 20. One more time is 100. So it will create a torque pulsation. So it will create a vibration. So pulsation could lead to undesired mechanical vibration. Okay, so we expect it to have a constant electromagnetic torque, meaning if 10 throughout the operation is 10, so we cannot like have different values because it will create an undesired mechanical vibration. We need to understand. So inside are physical components, physical part. When you have a mechanical vibration, after some time it will cause a wear and tear, overheated frictions, unwanted frictions, heat generated, and so many things. Okay, so we want to control that. Okay, okay, so how rotor start moving? So usually rotor will be stationary initially. Okay, so at time equals to 0, so rotor will be stationary. Stator supply switch on, and it will create a rotating field. Okay, so once the rotating electromagnetic field is generated, it will create a induced EMF in the rotor conductors, and the current flows in the conductor, and it will create so rotors will create a magnetic field. So the rotor magnetic field will follow the stator magnetic field. So it will create a force and also a, okay, so that is how a rotor start. Okay, so for electrical torque to exist, I think previously I covered this. So I've mentioned it a bit on the torque. So for torque to happen, the field must be distorted, meaning it must have a gap. Okay, so requires current in rotor conductors. Okay, so current required. So current depends on the EMF. Okay, so all this we understood. So EMF requires speed difference between rotor and field. Okay, this small speed difference is essential, and we call it as a slip. Okay. So the speed uh, will be a bit different. Okay, so let's say the stator speed is 10 radian per second. For a rotor, it might be maybe 9.8. So there will be slight speed difference. We call it as a slip. Okay, so this is the formula to calculate slip. And for most machines, the value of slip varies between 0.1. So no load meaning, so nothing is attached to the shaft of the motor. So usually it will be 0.01 and 0.10 at full load. So you can calculate the slip using this formula. So what if rotor reaches synchronous speed? So earlier I told you, so rotor and also stator will have some speed difference. But maybe we have the question, what if the rotor reaches the stator field speed? So if this condition happen, so no relative speed between the field and also the conductor, meaning there's no difference. So no current induced and no torque. And whether it's physically possible, no. So friction always slow down the rotor. So there will be a slight gap. Okay, this in the physical. So maybe in calculation you can calculate it to be the same, but in the real life it is not possible because friction will always slows down the rotor. Okay, so as a conclusion, rotor speed is always less than stator field speed and having a slip. So if we want to say, so rotor speed plus slip equals to stator field speed. So that is how we can conclude. Okay, so this is some formula to calculate the torque in the induction motor. Okay, so we can use this formula to calculate the torque. So all the descriptions are given below. So F is the frequency. Okay, and we also can calculate the power. Okay, and the mechanical power PM. So is a torque times with angular velocity of the rotor. So we can just replace the values and calculate. And we also can replace to form this formula. Okay, so depends on the information in the question. Okay, so we will see one example, short example for you to understand. Okay, so a three-phase 415 volt to pole 50 hertz induction motor as an effective stator. So rotor turns ratio of 2.2 to 1. So rotor resistance 0.15 watt per phase and also rotor standstill reactance 0.75 watt per phase. The motor runs at 2900 revolution per minute. Okay, so per minute. So rev over minute. So the question asks you to calculate per unit slip, torque, and also the mechanical output power. So you need to use the formula given previously. Okay, so per unit slip, so we know ns equals to frequency. So we want to find the slip as equals to 1 minus n over ns. So we can and replace. So s equals to 1 minus 2900 divided by 60 over 50, and we get the value 0.033, and we replace all the informations given in order to find the torque, and from here we can find the mechanical output. Okay, so you can try this, okay, example based on the formula given. Okay, so there's also a starting and maximum torque can be calculated, because torque, it can be three types. One is the starting torque. Okay, so previously we have seen starting torque is very important. Okay, so we have a starting torque, we have a maximum torque, and also we have a nominal torque. Nominal torque is the normal rated torque, or we call it as the rated torque. Okay, so here we can calculate the starting torque using this formula. So at starting, rotor speed n equals to 0 and slip equals to maximum 1. Okay, so you can replace, so you can get torque start equals to this formula. And maximum torque, so maximum torque is dt over ds. So this is the differentiation, okay, of the torque at the maximum speed. So you can just replace the value. So dt over ds, so it's always 0 at maximum, because it's already maximum, so no other changes. Okay, and when a equals to s, so you can simplify this formula to get tm is the uh, top maximum. Okay, so this is the formula. So maximum torque occurs when rotor resistance equals to rotor reactance. Okay, so you have the value of x and also value of r. Okay, so in the previous formula you can see value of r. So it must be equal in order to achieve a maximum torque. Okay, torque slip characteristic. So we can relate the torque and also slip using this curve. So this curve is torque versus slip. Okay, so you can see when A is the acceleration. When A is maximum, so you can see the graph is reducing. Okay, so reducing as the slip increases. Okay, torque will reduce. Okay, so when standstill, acceleration equals to sorry, when a equals to 1, maximum torque. Okay, slip is maximum 1. But you can see various accelerations. So acceleration equals to r quarter and also 1 over 8. So we can see from this graph, in steady state condition, induction motor with the smallest value of A. So out of all these A, this is the smallest, A equals 1 over 8, and it's a practically constant speed. So you can see constant speed and normal range of the machine. But we can see, even though it's a normal, is a constant speed, but it has a poor starting torque. Torque is only 0.3. So here also you can see it's poor. So not like acceleration maximum. Okay. So for motor to start, it's necessary that the starting torque more than the load. So if the starting torque is, so your load torque is, you attach something and it carries a weight. So you need to consider that as a load torque. So if your starting torque is not more than load torque, so the motor cannot rotate. So it's necessary for a motor to have a starting torque more than. Okay, so today we have seen practically about the induction motor and some of the principle behind the induction motor. I hope you have understood and please listen to back to this lecture note, especially in my YouTube. I will give you a puzzle for you to listen and for you to understand. Okay, so thank you.